Okay, there we go. So this is what we had yesterday, minus all of the extra sort of drawing stuff that we did. Yeah, so what do we have? We stated and proved the mean value theorem. So mean value theorem says, if you're continuous in the closed interval, differentiable in the open interval, same hypotheses as Rolle's theorem, right? That was exactly the same setup. Then there's some point in the interval, in the open interval AB, whose tangent line has the same slope as the secant line between A and B. And again, this is kind of the geometric interpretation. In practice, completely and totally useless. You don't use the geometric picture at all. But we did use the geometric picture in order to help us figure out how to actually prove this. So yeah, that was the thing. And I said, I think at the end of last day, that I would tell you why this is important. So there are kind of two reasons, and they're all going to stem from these two equations here. So these equations that actually show up in the statement, right, as the result of the theorem, that f of b minus f of a divided by b minus a is equal to f prime of c. Or alternatively, if you put the b minus a on the other side. And so what are the applications of this? So comment, right? Which is like, why do we care? Okay, because you're like, this is a nice theorem. Intellectually, I believe that this is a cool thing, but why does it actually win us anything? Why does it have a name? Why is it called a theorem versus just a proposition or something? Okay, and the reason for that, these are basically the same reason, but the perspective on them changes a little bit. So I mentioned last time, what it does is it gives you the ability to translate between the infinitesimal information, f prime, and f itself. Right? It's kind of like a Rosetta Stone in that way. It gives you a way of translating. Right? So it allows us to translate information between f prime and f. Okay, and I think that for this class, this will probably be the way that this is used most. It's not guaranteed. I think there will be a couple of ways that we use the second way, but this will be kind of the thing that we use the most here, right? The ability to translate information between f prime and f. Because, we have, if you look at the equation, we have f prime on one side and then a statement just about f's, no f primes on the left-hand side, right? So we've got f on one side and f prime on the other, and no limits or anything, right? No pesky limits that are going to get in the way. So we just have a literal statement between f prime and f. Okay, and then number two is it basically allows us to make approximations exact, right? So it allows us to make approximations exact at a small cost. Okay, so what I mean by this is the following fact. So we know, of course, the limit definition of the derivative, right? So we know that f prime of a, maybe let me just say we know this is the limit as x approaches a, f of x minus f of a divided by x minus a, right? And so it seems reasonable to say that if x is really small and is close to a, then if I drop the limit, I get a good approximation, right? So it's reasonable to suspect that if x is near a, then f prime of a is equal to approximately, well, here, maybe I shouldn't put the equals, is approximately f of x minus f of a divided by x minus a, right? And of course, this is actually an important thing. If you ever work with computers and need to actually compute a derivative, lots of times in real life, if you go on and you do applied stuff that isn't, pure mathematics, then you might be black boxed a function, right? So what that means is that you don't actually know what the function looks like it's a black box. Nonetheless, you can plug in a number and you can get a number out, right? So you don't know how the internal machinery works, but you can give it a number and you can get a number back out, and you can do that for any number. Interestingly, this does happen fairly often. You might then want to be able to compute, given a C, we can find A and B, so we can calculate them easy. Well, it depends what you mean by given a C, right? So anyway, let me say this. So one thing you might want to do is, if you have this black box functions, you might want to figure out what its derivative is, and you can't do it analytically because you don't know an expression for the function. So what you can do is you can approximate it, right? You can approximate it by computing f of x minus f of a divided by x minus a. And that should give you an approximation to the derivative of the function. Great, phenomenal. That actually turns out to be a bad idea in general. But what the mean value theorem says is that you can replace replace this, but this is the cost, right? So the mean value theorem says that f prime of c is equal to f of x minus f of a divided by x minus a for some x, or sorry, for some c in a x. Right, I'm kind of assuming here x is to the right of a. It doesn't have to be, but I'm assuming that it is, right? So it allows us to make this approximation exact. And this making this approximation exact is important in a pure mathematical framework, not just an applied framework, but in a pure mathematical framework, because there'll be lots of cases where you do, in fact, say, oh, look, I have this thing which is effectively the derivative, but I can't take limits yet. So what I'm going to do is I'm going to apply the mean value theorem, use that in order to turn this approximation, because I haven't taken limits, right? And until you take limits, it's just an approximation. So to turn this approximation into a statement about f prime and then apply the limit and then see what happens. So will we have an example of that today? Maybe, maybe not. But this is kind of the other big way that it's used. And as you get into higher mathematics, this is the sort of thing that'll come up. Now, Adam, given a C, can we find A and B? So no, and in fact, I think maybe even the more interesting question is the opposite, right? Which is, if you're given A and B, can you find C, right? Because the problem states that, you're kind of, what A and B are to begin with, and then there's some C that exists in this interval such that this is true. But the whole value of this theorem is precisely that, like, finding the value of C is generally impossible, right? It's so hard to do that it's not worth doing. And this theorem, the whole value of it is that you never have to, right? You're told that a value exists and you're done. So I can't conceive of a situation where you'd be given the C and then want to find the A and B. That's kind of a weird scenario. Maybe you could, but in practice it wouldn't happen. Usually the thing that we care about is, if you're given an A and B, can you find a C? And this is the sort of thing, right? When I was kind of talking earlier about how much I hate that they teach this in like 135, those are 100% the sorts of questions they ask. They say, here is a function on an interval A, B, find the value of C which satisfies the mean value theorem. And I would say to all my co-instructors, that is a stupid problem. That, like, don't give that problem to your students, because that defeats the purpose of the mean value theorem, right? Like, I mean, you guys haven't seen it yet, right? So you don't necessarily know what it's supposed to do, but the other professors know. And I say that's a really bad problem, because that completely undermines the point of the mean value theorem. If you can find the value of C, then you don't need the mean value theorem, right? The mean value theorem is important precisely because normally you can't find the value of C, but it guarantees that it exists, right? So it's an interesting question, Adam. I would say no to the question that you asked. I would also say no to the question that I stated, which is the rephrasing. And in fact, you've kind of hit like an important point about why the mean value theorem is so contentious when we teach first year calc. Now, for you all and for the MAT157 students, where we actually do proofs and stuff, this is a perfectly fine theorem to talk about. But in something like 135, for that reason, is usually something that we don't. Okay. So hopefully that clears that up. So this is kind of, these are the main applications. You can see there's no geometry anywhere in these main applications, right? So here, let me give you kind of the first two immediate results. And these two results, I think you're all probably going to be like, yeah, that's obvious, but it doesn't matter if it's obvious. If you can't prove it, it's not true, right? So now we can finally prove it. Actually, maybe I should call these Crawlery. So Corollary, if, let's just make the domain everything, if f maps R to R is differentiable, and f prime x is 0 for all x in R, then f is a constant function. Right? Oh, and actually, kind of to go back to what Adam was asking, again, when I say like we can't find the value of C, which matches for AB, and we can think about why that's true. The main thing that we write in order to prove mean value theorem, we prove Rolle's theorem. The proof of Rolle's theorem required the extreme value theorem. And you'll remember in the extreme value theorem, that is not constructive, right? When we prove the extreme value theorem, we assume for the sake of contradiction that no point existed, and then basically went about that way. So it did not construct the value of C, and that's why we can't do it, because it stems all the way back to the extreme value theorem. So that's kind of an interesting thing if you want to trace the lineage of that theorem. Okay, so this corollary, again, if your derivative is everywhere 0, then you are a constant function, right? The only things which differentiate to give you 0 are constants. Now you knew the other direction, right? If you're a constant function, then your derivative is 0, but this is the converse, right? So if your derivative is 0, then you're a constant function. Is there a constructive proof of EVT? No, yeah, there isn't, unfortunately, at least not that I know of. Because if there is, it means that you could use that proof in order to find extrema, maxes and mins, and finding maxes and mins are generally very hard. It's enough of a problem that we have entire research fields dedicated to just finding maxima and minima. So if EVT was constructive, that would be a game breaker, right? Like it would just unlock so much mathematics, it would be crazy. So it doesn't mean it doesn't exist, but it means that I am very certain that we don't have one. But it could exist, right? This is kind of the weirdness of mathematics. Okay. So like I said, I suspect many of you knew that this was true, but you actually need the mean value theorem in order to prove it. And you really do need the mean value theorem. This is pretty hard to prove without. And basically, here's how it's going to go. So I'm going to say fix x and y in R, arbitrary, right? And I'm going to show f of x is equal to f of y. Right? And this will have done it because what I'll have effectively said is that no matter what two pairs of real numbers you give me, they're all equal. And the only thing that can do that is the constant function, right? In fact, if you want, what you could do is just say, look, let's show that everything has the same value as 0. In fact, why don't we do that? Let's say fix x in real, and let's show that f of 0 is equal to f of x, right? So what we're then saying is for every x in R, it's just equal to the value of the function at 0, and therefore the function is constant, right? So I'm going to assume x is greater than 0, but the proof is the exact same for less than 0. Okay, so now what we're going to do is we're going to look at the interval 0 to x. So f is continuous on 0x, right? Because it's differentiable for every real number, which means it's definitely going to be continuous if you restrict it to any little interval. And for that same reason, differentiable in the open. And don't forget, you have to say both of these things before you can apply MVT or Rolle's theorem, okay? You have to say, look, my hypotheses are satisfied. I'm allowed to do this. Okay, so by the MVT, and if you want to say MVT, everybody knows what MVT means, right? Mean value theorem, you can totally just say that. So by the MVT, there exists some C in 0x such that f of x minus f of 0 is equal to f prime of c times x minus 0, which is just x. And now you see exactly where I'm going to use the fact that f prime of, that the derivative is everywhere equal to 0. This thing here is just equal to 0, right? So the whole right-hand side is 0, and we're done. And so f of x is equal to f of 0. Right? So again, this is what I'm kind of saying about it. It allows us to translate information about f prime into f and vice versa, right? Because I knew something about f prime, and I was able to use that in order to, infer information about f by using the mean value theorem, right? Information about f prime on the right-hand side of this equation. Hey, f prime is always equal to 0. That translated into now information about f and the fact that it was constant. Now, there's a very real sense in which you might look at this and you say, okay, well, that's a little tricky. And I think the first time that you use the mean value theorem, that's true. Because most of the theorems that we have up until now are fairly direct, right? In that you're walking down your proof road and you immediately come to an obstacle, and you've got your tool bag of theorems, and you know what theorem you're going to use in order to smash through that obstacle. Like it's evident. Here you can see we had to do a lot of setup to use the mean value theorem at the very end of that setup, right? And so we used the mean value theorem at the very end, and then it wasn't even direct, like somehow we didn't use all of the mean value theorem because we just ended up using this fact that f prime was equal to 0 in order to kind of get what we wanted. So it seems like a very indirect use, and I think that can sometimes throw students off. So kind of the best way to get around that is just to make sure you do a lot of mean value theorem examples in order to get a real hang for this. Okay, because yeah, I think that definitely tends to throw students off the first time. Okay, so we have this nice corollary. If your derivative's everywhere constant, or sorry, everywhere 0, you are a constant function. Okay, an immediate corollary to this, which I am not going to prove this one. So an immediate corollary, if f and g are two real numbers, sorry, real functions, such that, let's say, differentiable. Okay, so they're differentiable, and their derivatives are everywhere equal to each other. Then there exists some constant c in R such that f of x is equal to g of x plus c. Okay, I'm not going to prove this one for you. You can prove this one. It's a very quick, it should be 1 or 2 lines based off of the corollary we just proved. But it's nice because what it says is that if two functions have the same derivative, then the only way they can be different is just up to an additive constant, right? It's the only way two functions are different. So effectively it says, we haven't talked about antiderivatives yet, but we will eventually. It's going to say antiderivatives are unique up to a constant. Okay, so that's important, and the proof is an exercise. Okay, but like I said, 2 or 3, maybe 1 or 2 lines, right? It's pretty straightforward. The other one we're going to use, I think I called it a proposition the first time I introduced it, but I'm going to call it a corollary now because it is still a corollary of the mean value theorem. And it's going to be the statement that if your derivative is positive, you are strictly increasing, right? So if f, and again, I'm just going to make the domain R, but it doesn't really matter. Is differentiable, and f prime of x is greater than 0 for all x in R, then f is strictly increasing. Okay, and the proof is going to be almost exactly the same as the derivative being equal to 0 implies your constant proof, almost exactly the same proof. Okay, so I'm going to go through it pretty quickly. So what do we want to show? Let's just remind ourselves. So we want to show that if x is less than y, then f of x is less than f of y, right? That's what we want to show. That's what it means to be strictly increasing. Okay, so fix x and y real numbers. That's a bad. So w with x less than y. Now f is continuous. And unfortunately, like I said, you can't get around this. Okay, you got to state it every time, right? You got to show that your hypotheses work before you can apply the theorem. And differentiable on xy, right? And again, here I'm just using the fact that since I know f is differentiable everywhere, it's certainly everywhere continuous, right? Because differentiability implies continuity. So it's everywhere continuous. So definitely if I restrict myself to any subinterval of the real numbers, then it does everything that I want it to do, right? And differentiable on open xy, thus by the MVT. Don't forget to always say what theorem you're using. There exists some c in xy such that f of y minus f of x is equal to f prime of c y minus x, right? Okay, but f prime of c is always greater than 0. And y is bigger than x, right? Like we assume that, right? Y is bigger than x. So this is always also greater than 0. So this whole thing is greater than 0. And now if we just move that to the other side, we get f of y is greater than f of x. And that's what we wanted. Right? So very, very similar proof, right? You can see it's almost identical right up until that very end. But instead of using the fact that f prime of c is equal to 0, this time we use the fact that it's strictly positive, and then again, move, f of y to the other side or f of x to the other side, however you want to do it. And voila, we're done, right? Now, they're not all going to be that easy, but this is kind of a nice warm up to show you like how it is the mean value theorem actually works. And like I said, this is kind of an, of the two main applications I said of the mean value theorem, these are all examples of number one, right? Where you're translating information about f prime into information about f. So I got a direct message here. Just give me a second to read it. Yes. Yeah, Adam, exactly. Perfect. Okay. All right, so that's going to take care of that. Now let's do something a little bit more interesting. I'm not going to prove all of these because there's a million of them, but I'm pretty certain some of you have heard about this theorem. All right. Who's heard of L'Hopital's rule? Yeah. Did anyone see the proof of L'Hopital's rule? Oh, nice. Okay. Okay, sure. I mean, the proof is not, it depends, right? So the proof technically uses something called Cauchy's mean value theorem. What we're going to do is, instead of proving Cauchy's mean value theorem, so you can just prove Cauchy's mean value theorem from the mean value theorem. It's no problem. I'm basically going to prove Cauchy's mean value theorem as part of the proof of L'Hopital instead of introducing it as a separate result, because in my experience, the only thing that I've ever seen Cauchy's mean value theorem used for is the proofs of L'Hopital's rule. Now, there are about 1 million different versions of L'Hopital's rule, right? if you've seen L'Hopital, you know that there's like the 0 over 0 form, which is what we're going to do. There's also infinity over infinity. There's like, whether one function diverges or not, the one-sided versions, it's a whole big mess. So I'm just going to do 0 over 0 because I think that's the most useful one. What do you mean by sequences? Like we'll do sequences eventually, but we're not going to use them here. Did you use sequences when you saw a proof of this or something, or? I read a proof, but oh yeah, okay. I mean, I suppose it's possible. Yeah, I mean, like, I don't think I've seen a sequence proof, but I suppose you could. The problem is that there isn't a good characterization of differentiability in terms of sequences. There's a good characterization of continuity, because sequences naturally play with continuous functions very, very nicely. With differentiable, though, it's slightly different, right? You don't get something nice there. So it'd be kind of interesting to see. Also, sequences at best can pick up discrete information about a function versus functions which actually have continuous information, right? Because you have an entire interval's worth of information. I was going to say info, and then I cheaped out halfway into saying information. So if f and g are differentiable at C, and then both the limit as x approaches C, f of x is equal to 0 is equal to the limit as x approaches C, g of x. And I know that's probably too many ands, but whatever. Exists, then f prime of x over g prime of x. Okay. So it says if, and again, I think normally when this is kind of taught, because you might spend a couple of units on it, right? You might spend a couple of weeks talking about L'Hopital's rule. You usually introduce these sort of like things called indeterminate forms, right? And so you talk about something is indeterminate, a limit is indeterminate form 0 over 0 if the limit of the numerator and the limit of the denominator are both 0, wherever you're trying to do the limit, right? So you can see that's built into the theorem statement because you know that limit of f and the limit of g are both 0. Now, an important point, of course, here is that you also need to know that the limit of f prime over g prime exists ahead of time, right? If that thing doesn't exist, then there's really nothing you can say here. I mean, there is, but you have to prove a different version of this theorem. So we're proving if the limit of f prime over g prime exists, then in fact, the limit of f over g is the limit of f prime over g prime. And this is crazy, right? Like the fact that this works out is nuts. This isn't a quotient rule, right? We're not applying the quotient rule on the right-hand side. We're literally just saying, take the derivative of the numerator, take the derivative of the denominator, do that separately, and then evaluate that limit, right? And if you get a number out, boom, that was the limit of the original thing. So that's really, really nice. Let's prove this now. And the reality is I'm going to show you, by the end of this course, there's sometimes we don't prove L'Hopital in this course. And the reason is that it's useless by the end of the course. Because by the end of the course, I will teach you a much, much better way of doing these sorts of limits without L'Hopital's rule. And like L'Hopital's rule is actually really inefficient and slow compared to computing limits that way, right? Like I can compute limits using the way that we're going to learn at the end of the course. I can do it in my head. And then if I have to use L'Hopital's rule, it'll take like 5 minutes. Okay, so I'm going to show that to you by the end of the year, or the end of the course, but we're not there yet. All right, so here's how the proof's going to go. So I'm told that f and g are differentiable near C. Let's just be technical and let's say let delta greater than 0 be such that f and g are differentiable. Let's call it delta 1, are differentiable on C minus delta 1, C plus delta 1. Okay. And then the other thing that we're also going to use is in order, like we really want G prime to not be 0 as well, right? And the fact that this limit here exists means that G prime of X must not be 0 in some neighborhood near C, right? So let's say let delta 2 such that G prime of X is not equal to 0 on C minus delta 2, C plus delta 2. And then I'm just going to take the min of them so that I can guarantee both of these things are true. Min delta 1, delta 2, right? So now, like I said, if I'm on, C minus delta to C plus delta, both facts are true, which is nice. So basically what I'm going to do is I'm actually going to prove that this holds in the one-sided limit. Okay, so I'm going to prove that this holds as X approaches C from the right. From that, the proof for approaching C from the left is almost identical. And then, first of all, we'll have one-sided versions of L'Hopital's rule, and the two of them combined will give us the two-sided version. Okay, so maybe let me say that first. So we're going to prove, we'll prove the theorem as X approaches C from the right. The proof for X approaches C from the left is nearly identical. And so again, as a bonus now, we're actually going to get one-sided versions of this theorem, right? Because right now the theorem statement is actually a two-sided limit, but it turns out because we're going to prove the one-sided versions, we're going to get the one-sided ones for free. Okay, so suppose that H is in 0 to delta, right? And what I'm going to do is define, actually, I guess I could have defined these functions first. So define capital F to be, what do I want here? I want f of X if X is not 0. You might say, why am I doing this? I'll tell you in a second. Okay. So this is kind of silly. This part really, I mean, technically you have to put it here, but it's not critical to the proof. The thing is, okay, if you go back up here and you look at the theorem statement, we've got this statement right here, right? So we know that the limit of f and the limit of g are both equal to 0. Now, that doesn't tell us, and the functions are both also differentiable at c. I guess we could say that we know that f and g are both continuous at c. What do I want? Or sorry, I guess this should be c, not at 0. I'm not taking the limit at 0. So this is just to guarantee that these functions are actually continuous. Maybe I don't need differentiable at c. Maybe I only need differentiable near c. I guess, yeah, actually what I only need is differentiable near c. So let's change that in the proof. Right? So I don't actually know they're differentiable at c. I'm just going to assume that they're differentiable in some neighborhood around c. So in which case, I'm also going to change this to c union c, c plus delta, right? Deleted interval. So now capital F and capital G guarantee that my functions are in fact continuous, right? Because I don't know what they actually do at c, right? The limit here, the limit of f of x being equal to 0 doesn't guarantee that f is continuous at 0 because it can do, or at c, because it can do whatever it wants at c. So we're going to define capital F and capital G just to plug in that removable discontinuity to make sure that everything is kosher, right? Capital F and capital G are now continuous. So note that capital F, capital G are continuous at C and differentiable on C plus delta, right? Because we assumed that they were differentiable on C plus delta, right? Because these are just equal to F and G on that interval, and we assume that those are differentiable on C plus delta, okay? Okay, now here's the part where we prove Cauchy's mean value theorem. So we're going to define a third function, h of x. So this is going to be, let me make sure I put them in the right order here. Yeah, okay, f of x, g of c plus h. So this is a constant, right? Minus g of x, f of c plus h, okay? So again, this h here is continuous on, on c to c plus h. Right? Because both capital F and capital G are continuous on that interval by construction. And this is just some constant times F minus some constant times G. So it's the, you know, it's a linear combination of continuous functions, is therefore continuous itself. And for the same reason, H is also going to be differentiable on the open interval. On C plus H, okay? And just so you can guess what we're about to do, we're about to mean value theorem this thing. The other thing that we should check while we're here is just what is H of C and what is H of C plus H, right? Because I'm going to need those when I apply the theorem. Okay, so H of C is going to be equal to, should be equal to, oh yeah, it's equal to 0, definitely. Well, here, let me make that clear why. Okay, this thing here is equal to 0, and this thing here is equal to 0, right? That's the definition of what capital F is, right? The capital F is equal to 0 at C, capital G also equal to 0 at C, right? If you look at their piecewise definitions up there, so that whole thing is equal to 0. And then H of C plus H is also equal to 0, just because you get both F of C plus H, G of C plus H in both terms, right? Right, the two terms here are the same, so they're going to cancel out to give you 0. So in fact, we don't even need to use the mean value theorem here. We can just use Rolle's theorem. But we're not going to refer to anything by Rolle's theorem anymore. It's just the mean value theorem. So by the MVT, there exists some C in, oh no, I've already used C. I don't want to use C again. Some theta in C plus H, such that H of C plus H minus H of C is equal to H prime of theta times H, right? Now, everything on the, or in particular, if we were to directly apply Rolle's theorem, we know that this thing is equal to 0. This thing is equal to 0. So that implies H prime of theta is equal to 0, right? But again, H prime, if you look at the definition of H prime way up here, right? And the fact that F of C plus H, that's also a constant. So when it's easy to differentiate this thing, right? It's just going to be capital F prime minus capital G prime. Zero is H prime of theta, is capital F prime of theta, G of C plus H, minus capital G prime of theta, F of C plus H. So what I can do is rearrange this, and what will I get? I will get F prime of theta divided by G prime theta is equal to f of c plus h over g of c plus h. And in fact, since none of these are equal to c, we can actually just rewrite this now as f prime of theta over g prime of theta is f of c plus h over g of c plus h. Okay. Now what we're going to do is we're going to take a limit as h approaches 0 from the right. As h approaches 0 from the right. But note that because theta is in c plus h, that also forces theta to go to 0. Oops. Or rather, theta to go to c. All right, so we have c is less than theta is less than c plus h. So by a squeeze theorem sort of argument, if h goes to 0, then theta must go to c. So theta approaches c from the right as h approaches 0. Right? So this means that we get that the limit as x approaches c from the right, f prime of theta, g prime of theta is equal to the limit as h approaches 0 from the right, f of c plus h over g of c plus h. And of course, that limit right there is the same thing as the limit as x approaches c from the right of f of x over g of x. And if we strip out that middle bit, oh, sorry, this should be theta here. That's exactly L'Hopital's rule. Right, and of course, it doesn't matter that you don't use x's on both sides of the equation. That is just a dummy variable there, right? So we have that the limit as we approach c from the right of f divided by g is the limit as we approach c to the right of f prime over g prime, right? And again, x and theta there are actually different, right? They're kind of playing a different role, but it doesn't matter because as you take the limit, like you don't care about what the actual relationship is between x and theta. All you care is that as you limit towards c, you end up getting the same set of limits, right? And so there you have it. We've now proved L'Hopital's rule as we approach c from the right. You can imagine that the proof as you approach c from the left is pretty much the same, right? Like there isn't, like what's going to change? Is anything here going to change? So you still define f and g the same way. They're still continuous and differentiable on c minus delta to c. Yeah, I mean, like pretty much nothing changes, right? It's almost exactly the same result. The only reason that we really do it this way is because we want to be able to, just kind of look at this and not have to say, oh, well, if theta's in the left side, then it approaches from the left. And if theta's in the right-hand side, it approaches from the right. You don't want to kind of have to do both those at the same time. So you just say, okay, let's pretend that we're just on the right. That way we can guarantee that theta approaches c from the right as well. It's just going to make the language a little bit easier. Obviously, it would actually be more work if you had to write out the entire other side of the proof, but it is fine to say, look, the proof when, the proof as we approach c from the left is exactly the same, right? Mutatis mutandis, just make the appropriate changes and it's the same proof and you don't have to do it. And again, as a benefit, we also get the one-sided versions of L'Hopital here. Now, believe it or not, the proof of the infinity over infinity indeterminate type, so it's the same theorem statement, but instead of f and g going to 0, they go to infinity. That is a fundamentally different proof. And you see that it has to be because we really leveraged right here the fact that our limits went to 0, right? So the infinity over infinity proof is actually different. It's actually, I think it's a little bit more complicated, but the theorem is actually stronger because you don't actually need both limits to go to infinity. You only need one of them. So if anybody's interested in that, if you have, my copy of the book, it runs you through that proof, so you can see it yourself. But like, we're not going to worry about it here because we're almost never going to use it, right? I kind of need this in a second, which is why we did it. Maybe let me do a really quick example to show you L'Hopital at work. So the great thing about L'Hopital is that if you need to apply it multiple times, like to take many derivatives, you can do it as many times as you like. So find the limit as x approaches 0. What did I choose here? Tan 4x minus 4x, all divided by 16x cubed. Okay, and again, you can imagine this is probably pretty tough to do, but with L'Hopital, it ends up becoming much quicker. All right, so both numerator and denominator clearly go to 0. Limit to 0, right? Now, technically, we can't apply L'Hopital's theorem. What we'd have to do first, strictly speaking, is compute the derivatives, check if that limit existed, and then say by L'Hopital it's equal to this limit. In practice, that's way more writing than we actually want to do. So what you do is you just start writing it down and hope that eventually you get to a limit that exists, and then argue that by repeated application of L'Hopital, you get what you want. So let me show you what I mean by this. Okay. Now I like to, this isn't universal, but I like to just, when I've used L'Hopital, I like to indicate it like this. Okay, so I'm going to differentiate tan 4x, which is going to give me what? So 4 secant squared 4x minus 4. And then if I differentiate 16x cubed, that's 48x squared. So let me just do some cancellation here. So that's going to give me what? Secant squared x minus 1 divided by 12x squared, right? It's still 0 over 0, right? So I'm going to apply L'Hopital again. And again, as far as we know, this is kind of like rough work, because if you eventually get to a limit that doesn't exist, none of this was valid. But if you do eventually get to a limit that does exist, it's okay. So I'm going to L'Hopital again. Oh, shoot, this should be secant 4x, sorry, secant squared 4x minus 1. Okay, so the derivative of secant squared is 2 secant x squared tan x, right? And then I multiply by 4, so that's going to be 8 secant squared 4x tan 4x. The derivative of 1 is just 0. This is going to give me 24x here. So again, I can do a little bit of simplification. So secant squared 4x. I keep forgetting the 4x. Tan 4x all divided by x. Still, it's 0 over 0. So we're going to do L'Hopital one more time. And this is what I mean by, it takes me like 5 minutes if we do this with L'Hopital, but I could have done this one in my head. Okay, so the derivative of secant squared is again going to be secant blah. Oh my God. Okay, so what is this going to give me? So the derivative of secant squared is going to be 8 secant squared 4x tan squared x, right? Plus the secant squared times the derivative of tan. So we're going to get what? 4 secant to the 4x divided by 1. I guess I don't need to put that in. This limit now exists as we go to 0. Oh, sorry. Why did I need the 3 here? So this will give me divided by 3. And now the tan goes to 0. The secant to the 4 secant. Sorry, I forgot my 4x's again. It goes to show you how often I do computation. Secant is 1 at 0, right? So I'm going to get 4/3 like this. And I'm done. Yeah, Mary, yeah, thank you. I missed it because I wasn't looking at the chat, but you're right, it is 3x. Okay, so again, and just to be very quickly clear, once I get to a limit that exists, I say, oh, now I legally was allowed to use L'Hopital. So, and then I kind of would chain my way back upward. So if you wanted to write it out really rigorously, I'd say, look, this very bottom one is equal to this one, right? And then I know that this limit exists because it's equal to this one, and I just showed that it existed. And then I know that this one exists because its derivative is this, and I just show it existed. But who actually wants to do that, right? Like, that's silly. So in practice, if you do want to or are forced to use L'Hopital, just apply L'Hopital, hope that you get something that works in the end. That's perfectly legal. That's what everyone does. And that's how you would do it. Okay. What a mess, though. As you can see, I really didn't have a good time there. I was forgetting 4 X's and 3's everywhere, because don't ask me to do any computation. I can't do it. But yeah, there you go. Okay. So we will, we're actually going to start something a little bit interesting next week based off of this. Your next assignment is up, but I think we're going to need one of the results of the assignment. So at the very least, you should read it, even if you haven't proven it. I think it's the first question from assignment 7. I don't remember it's the first or second one. But the first question from assignment 7 is something that we're going to use next week. So make sure at the very least, you just give it a read and understand what it says, right? The proof isn't actually that hard, but we are going to use that. I'm going to refer to assignment 7, question 1, or whatever question it is. So just give it a read so that you know when I refer to it, what I'm talking about. Okay, any questions? Everyone's happy? Okay, cool. Then as far as I'm concerned, we're good. We're done for the week. And we can call it there. Everyone have a good weekend. If you have any last minute questions about the assignment, don't hesitate to throw them on Discord or Piazza. We'll answer them there. And otherwise, yeah, have a good weekend. And I'll see you on Monday or Tuesday, depending on whether you come to office hours. Let me stop the recording.